You good?
Yeah.
All right, so restarting.
It was awesome, by the way.
Back when that.
Traumatized her for life, but you know, I'm interested. And I got to go do a cricket one time.
Did I ever talk about the blood samples we did in high school?
No.
Back when you could do human blood samples. So we were trying to do blood samples so we could test to see what kind of blood we had. And my lab partner was sticking my finger and no blood was coming out. So he said, Mr. Sterner, I'm having trouble getting blood. So Mr. Sterner comes out over, squeezes my hand like that, takes the sticky thing. What is it called?
Needle.
No, there's another name for it.
Butterfly needle.
Takes the butterfly needle, goes boom.
No.
He got blood.
Oh, but that hurt.
What?
Did that hurt?
Oh yeah.
I would.
Butterfly needles are the freaking worst. It's like getting a fish hook caught in your skin. Which has happened to me, by the way. So I know what it's like.
All right. So we last left off.
PBNRT, little n.
We had PV equals nRT. It's the ideal gas law from the chemistry point of view, or big N kBT. This is Boltzmann's constant. R is the ideal gas constant. This is the number of moles.
And T equals time, right?
T is temperature.
Oh.
Big N is number of molecules.
Is it PV as in speed or PV as in
Pressure and volume, I believe.
Yeah.
volume? Okay, I just didn't know.
Serif of the V. Through the other derivation that we had done, we leave it as pressure equals or as force equals. I can't remember what I had written on the board.
I don't think we really got that far.
There was something written over here, I know that.
You wrote that on there. And
That,
then
okay.
class ended.
Oh yeah, you wrote like P equals 2V squared NM over 3
Okay,
volume.
that's it. What was that again?
P equals 2V squared, capital N and then M over 3 volume.
Okay. Through our model of particles in a box, we ended up with the pressure on a side of the box would be equal to this. From the ideal gas law, we have what we have there on the left. Now, ideal gas, the molecules will have perfectly elastic collisions with the wall. In other words, when the particle hits the wall, the wall does not heat up at all. And the other thing is that the particles do not interact with each other. So a lot of phasing through each other. There's a modified aspect of it which takes into account the size of the molecules and their interaction with each other, called, if I'm calling correctly, van der Waals gas law, but
Dr.
we're
Fox,
assuming ideal for now.
for the K on the screen, on the board, what's
Yes,
the little subscript? Is that a B?
that's a B for Boltzmann.
Is there any other K law?
Well, we have K, the lowercase k that we use for
Okay.
the spring constant.
Okay.
All right, so if we multiply this equation on the right by the volume, we end up with 2v squared nm, which would be equal to this, assuming an ideal gas. In other words, the molecules in the box have to be sparse enough so that the particles are not really interacting with each other for any significance. So we combine the two equations. and I get N kBT is equal to 2/3 V squared N. Obviously, the number of molecules cancels out. If I multiply both sides by 3/2, if I could lost a fraction here somewhere, just a second. You see someone's notes.
For what?
Something's wrong with the number there. Just do a silly thing there. Let's see, so multiply factor of 2. Oh. All right. Dang it. If you think back to when we had the box, and I was talking about within a certain amount of time t, you have only a certain number of particles that actually are going to be hitting the wall over here. Statistically, okay, I have a certain within the right amount of speed, or even just the horizontal component times time, but half of those are actually heading towards the wall, and half of them are heading away from the wall. That half I ignored. So there actually should be an extra half in here. That 2 should go away. It's half the number that I had said. And I know that's not the ideal way of going about it, but there it is. If I multiply both sides by a half now, so I'm down to here that mv squared is equal to 3 times the Boltzmann constant times the temperature. If I multiply by half, I get 3/2 kBT is equal to 1/2 mv squared. And where have we seen that before?
Kinetic energy.
So the temperature of an object is, sure. No, that is right. So we can leave it, different ways of expressing the same thing. So it's 2/3 kinetic energy over Boltzmann's constant, or the kinetic energy is equal to this. But what this is showing is that the temperature is directly related to the average kinetic energy. Because I made references before about if I slide something on the table, that it's going to lose energy, the energy goes to the table will heat up. the kinetic energy that's lost from an object I slide across the table. If we figure out how much kinetic energy is lost, we can then predict how much the temperature, in essence, what the temperature change is in the table.
Dr. Fox, can you explain the equation above the box?
The equation above the box.
Yeah, how do we get M?
How do we get M? That was going back to what we had before. Oh, before we were looking at the impulse and the momentum, and momentum has mass in it. That's where the M comes from.
So the top part of the formula is,
A combination of several things that we did last time. We had a certain number of particles in here. We looked at we looked at the impulse acting on the wall, which would be the negative, the impulse acting on the particle. Impulse is equal to the change in momentum for force times time.
okay.
I feel like basically you have to rederive everything we did on Thursday.
Okay.
And you're fine with that, or you will accept that?
I'll accept that I'm not understanding and I probably won't change on screen recording.
Okay. Afterwards, I'll
Cool.
go over it with you if you wish.
Yes, please.
And Boltzmann's constant. I was hoping I had it written down, but we can figure it out. It's a mole.
A mole? Yeah, no, that's mass. This is just a free throw. The amount of substances, like the amount of stuff in a thing, like density almost.
No. It's simpler than that.
The number of molecules in it.
Simpler than that.
Molecules.
Simpler. I don't know why I'm getting quiet. What's a dozen?
12.
What's a score?
1,000. 100.
20.
Okay. Well,
Gettysburg Address, 7 years ago. Basically,
I don't.
87
I
years
don't
prior.
confine myself to memorizing that.
That's all. Anyway, a mole is just a number. Like a dozen is 12, a score is 20. A mole, it just happens to be a really big number.
Do you want me to tell you what that is?
6 point. So a mole,
6.022 times 10.
I was just going to go to 10 to the 23rd.
Yeah, I guess. I mean, it didn't show up on this for some reason. Let me go.
Now, how Avogadro came
Yeah,
up with that,
23rd.
that is Avogadro's number. How he came up with it, I don't know. But he did, and it seems to be somewhat of a standard. And it's often labeled as N sub A, sometimes referred to as Avogadro's number. If we look at the periodic table, and we just need part of it. If I have a mole of oxygen, then I will have 15.9994 grams of it. So the number here, the atomic mass, is the mass in grams if I have a mole of this amount of substance. So if I have 6.02 times 10 to the 23rd oxygen molecules, I've got a mole of it. In other words, this little n would be 1. So little n, the number of moles, is going to be the number of molecules divided by Avogadro's number. Ooh, now we're going to be faced with what is the ideal gas constant.
Uh, 8.314 joules per, times moles.
Joules
times
moles?
moles. To the negative one, I guess.
Joules per mole?
So according to science notes, it says R equals 8.314 joules per inverse K times mole inverse.
Okay, so the unit it is joule, K inverse, mole inverse,
Oh yes,
that's it?
yes.
Okay, so that's, oh, there's a fraction in there, 8.214 joules per Kelvin mole.
No, it's joules times Kelvin mole.
But Kelvin and the moles would have the negative one.
That's
Did it?
Oh, so yeah.
Oh, because the negative one. Sorry.
Alright. So since temperature is the same here, I know that little n big R must be equal to big N KB. So little n big R must be equal to big N KB. I'm trying to solve for KB, so KB is equal to little n big R over big N. I know that the number of moles divided by the number of molecules would be, well, in essence, well, from here, little n over big N would be 1 over Avogadro's number. So this would be the ideal gas law divided by Avogadro's number. So that's 8.214 joules per Kelvin mole divided by 6.02 times 10 to the 23rd. So not make a careless error. And that is?
That's in calculator.
1.36 times 10 to the negative 23rd power. Wouldn't it just be J over K times?
Sorry, you faded.
Isn't it just J over K times moles? Or is it just J over K?
It actually, it's gonna end up being J over K. The mole here, this is 6.02 times 10 to the 23rd per mole.
Yeah, okay.
So the moles would cancel out. Anyway, Boltzmann's constant. But the main takeaway I wanted you to have is the fact that there's a connection between temperature and kinetic energy, which had been alluded to before, but now we have some mathematical evidence to support that.
Because it's per mole, but it's yeah. Since it's 1 over NA, can you tell me why 6.02 times 10 to the third is like this is 1 over mole and not just 1 mole?
Dr. Fox?
Yep.
Your R is wrong. It's 8.314.
Grade 1-4?
Yeah.
Which will change that.
Yeah, that one.
1.38.
38. All right, let's see. So if something costs $5 a dozen, USD for US dollars. And the reason I didn't stick the dollar sign in front, as is traditional, is I wanted the units sort of congregated together. And then I have, I'm buying 24 objects. Is this analogy gonna work? Oh, I got a better way of doing that. Okay. Let's get rid of this stuff.
Dr. Fox?
Yep.
Boltzmann's law. Which
Well,
is,
it's constant.
sorry, Boltzmann's constant. Is that a negative 23 exponent?
Yes.
Okay.
All right, so we have 8.314 joules per Kelvin mole. A mole is just a number. It doesn't, what threw me when I first dealt with moles is it looks kind of like the abbreviation for molecule, but it's just a number. Therefore, that's the same as 8.314 joules per Kelvin times 1 over moles, which is 8.314 joules per Kelvin times 1 over 6.02 times 10 to the 23rd. That's why the moles can disappear. Does that
Yeah.
work for you? Is that work for you? Yes. We speak English. Does that work for you? Robin, you look like you want to say something.
Can you just divide